Hello, this is Jack Jackson. We're going to continue to look at some optimization problems. The next few problems we're going to look at have something to do with some geometric properties, and actually they're kind of a manufacturing type examples as well. So suppose we have 30,000 cubic centimeters of material, and it's available to make a box with a square base and an open top. Find the largest possible volume of the box and dimensions which will produce that box. So if we introduce variables in our solution, we need to clearly state what those variables represent. So we're going to let S be the length of the side of the square base. So the area B, capital B, is the area of the base, which is just going to be S squared. H is the height of the box. V is the volume of the box, and A is the surface area of the needed materials of the box, which we know we're going to use all of them if we're going to maximize it, so that will be 30,000 square centimeters. So the surface area, if you think about the way the box looks, it may be useful to draw a picture. Here's a picture. We have a square base, we have a height here, and I believe this box is an open top, so there is nothing here at the top, but we have material around the four sides and the bottom. So each of these four sides has height S and base little s, height H, and base S. So it's H by S, so it's H times S, and we have four of those. So it's 4SH for that area, and the area of the base is S squared. Okay, but the total, add those together, we get the total area, which is 30,000 square centimeters. Let's see what I'm going to do next here. I'm going to solve for H. So I'm going to subtract S squared from both sides, also switch sides here. Then I divided both sides by 4S, and I distributed it. So 30,000 divided by 4 is 7,500, and then that 1 over S is S to the negative 1. S squared divided by S is S, and of course negative 1 divided by 4 is negative 1/4. So there's the height as a function of S. The volume is the area of the base times the height, or in other words, S squared, length times width times height, or S squared times H. But H is given by this formula, so I can substitute that in. And now we have the volume as a function of a single variable. I'm going to distribute the S. S squared times S to the negative 1 is just S, and S squared times S is S cubed. So here we have the volume as a function of S. So remember, that's one of our basic milestones in the solving of the problem, is to come up with a formula for the thing that we're trying to maximize. We're trying to maximize volume. We want it in terms of a single variable, which is exactly what we have here. So we can optimize that now by taking the derivative. So take the derivative with respect to S. This part here is just 7,500 since that's linear. And this is 3 times negative 1/4 is negative 3/4, and the power goes down to 2. So the derivative is pretty easy there. It's just a polynomial. Set the derivative equal to 0, and we want to solve this. So here we can add 3/4 S squared to both sides. Multiply both sides by 4/3 gives us 10,000 here. Then take the square root. S is plus or minus the square root of 10,000, but S cannot be negative in this context. So in fact, S is positive square root of 10,000, which is actually 100. So S is 100 centimeters. Now go back to the height function right here and plug in S is 100. So this is 7,500 times 100 to the negative 1, or 7,500 divided by 100, which is 75. Minus 1/4 of 100. 1/4 of 100 is 25. 75 minus 25 is 50. Of course, you can do that in your calculator if you want, but there we did it by hand. So that's 50 centimeters there. And of course, the volume is 100 squared times 50 is 500,000 cubic centimeters, and that is a pretty good sized box. But that's the maximum you can make a box with that amount of material. Of course, the volume is measured in cubic centimeters, and the lengths of the edges, the sides of the S and the H are both in centimeters, and of course the square centimeters for the surface area right here. All right, here's another one I like to do a lot of times. A typical soda can holds 355 milliliters. That's 12 fluid ounces. And it's roughly in the shape of a cylinder. So let's assume for the moment it's actually a cylinder. And the thickness of the top of the can is 3 times as thick as the sides and the bottom of the can. Why? It's to accommodate the pull top. If the top was as thin as the sides, when you did the pull top, you'd probably rip the can. So what dimensions will minimize the amount of aluminum used in the production of the can? So here we've got our picture of our cylinder. We have a radius R right here, a height H. Now the volume is fixed at 255 milliliters. What is a milliliter? Well, a milliliter is a cubic centimeter. Okay, so that's an appropriate volume unit, whether it's milliliters or cubic centimeters. We're going to think of it as cubic centimeters. Now we have a relationship between radius and height of the cylinder because the volume of a cylinder is the area of the base times the height. That works for a cylinder or a prism. The area of the base for a circular cylinder is pi r squared. So a right circular cylinder, the area there, the volume is going to be pi r squared times h. Okay, well, solving for h is the volume divided by pi r squared. The volume is a fixed amount of 355 milliliters. No, that should say 255. Oh man, I hope I didn't mess this up. 255. Is it 255 or 355? Okay, so I picked up a can and looked at it. It's actually 355 milliliters, so it was right in the original problem. It's right actually all the way through. It's just right here. I had the wrong thing right here, so that's good news. Okay, so anyway, the height is 355 divided by pi r squared. Notice r is in centimeters. The top is in cubic centimeters. This will all work out to be centimeters, which is appropriate for the height. Now the volume of aluminum, the amount of aluminum used is actually a volume, but it's really based on the surface area. So T is the constant thickness of the sides and the bottom, so 3T is the constant thickness of the top. So the top and bottom are the interiors of circles, circular discs, and each have an area of pi r squared. If we slice this side and roll it out flat, the side is a rectangle. So we have basically more or less we have a rectangle and two circles put together. Roll up the rectangle, put the circles on the top and bottom, and we've got our can. Now when you unroll this, the rectangle that we get is going to, the width of the rectangle is going to be the circumference of the circle, which is 2 pi times the radius. Okay. So, what do we get for the amount of aluminum? So A is the amount of aluminum, which actually is a volume. So it's 3T times the area of the top, plus T times the area of the bottom, plus T times the area of the side. Well, the area of the side is 2 pi r for the width, and the height is h. So it's 2 pi r h. The area of the bottom is pi r squared. The area of the top is pi r squared. Okay, so I'm going to combine the first two here, and that's they both have a pi r squared and a t, so we just add 1 plus 3 there to get 4 t pi r squared. And the second part is 2 t pi r h. And but now h is 355 over pi r squared. So let's see, let's do a little simplifying here. This is 4t pi r squared for the first part. 355 times 2 is 710, and we still got a t, and we got r over r squared. Well, the pi's cancel here in this part, notice. And the r over r squared is 1 over r, which is r to the negative 1. So now we have a as a function of a single variable r. T, however, remember, is a constant. It's not changing if we change the radius. We don't know what it is. It's something pretty small, the thickness. Alrighty. We can now take a derivative. So once we've found a formula of the thing we're trying to minimize, we're minimizing this A, the amount of aluminum. Once we get it as a terms of one single variable, then we can take a derivative. Remember, T is a constant, as is pi and 4. So this is 2 times 4t pi, that's 8t pi times r. This is negative 1 times this is negative 710 t r to the negative 2. And so you want the derivative and set it equal to 0. And notice the first thing, I'm going to multiply both sides by r squared over 2t, which still leaves us a 0 on the left. And if we do that, look what happens here. So the 8 divided by 2 is 4. We still got a pi. R squared times r is r cubed. And that gets rid of this negative exponent here too as well. So 710 divided by 2 is negative 355. The r squared times the r, the negative 2, cancels out, and the t cancels. So notice the thickness actually doesn't matter. The optimal shape of the can is not going to depend on that thickness that we make everything. It did matter that the top was 3 times as thick as the sides and the bottom, but it really didn't matter what that thickness is. So luckily we don't have to know that to work the rest of the problem. So then continue to solve. We add 355 to both sides, divide both sides by 4 pi. That's r cubed, so r is the cube root of that, or the 1/3 power. Approximate that. That's about 3.05 centimeters. And if you plug that back in the original formula up there, or the formula that we found for h, right here, 355 over pi r squared, you get that the h is about 12.2 centimeters. Now, I tell you, go pick up a soda can and measure it, and you'll find out that it's extremely close to that. The radius of 3.05, or a diameter of about just a little over 6 centimeters, about 6.1 centimeters, is almost exactly right for a soda can. Now, over the years, they've modified this a bit by curving the bottom of this top and making it not completely flat. They also pulled in the top a little bit since that extra thickness is on the top. They saved some money that way. That also made it better to stand up. It also made it a little bit more structurally solid and strong. So what do you think? Do you think the designers of a can know calculus? You bet they do. And they use it regularly to save the company money on production. So in general, this idea of just things like packaging here in a marketing situation, a manufacturing situation, you can save a company, like Coca-Cola or Pepsi or something that makes lots of cans of soda, and they're gonna, if you can save them just a small fraction of a cent on a can, it's going to make them a lot of money in the long run because of their volume of production. So, this idea of packaging and knowing something about calculus can make a big difference. So here's another problem that's actually extremely similar to the one we just did. Okay, I'd like you to work this one on your own and see if you can get the answer, and then come back and check your answer with me. A man is building a storage silo in the shape of a cylinder, that is a right circular cylinder. The cost of the concrete floor is $6 per square foot. The cost of walls is $5 a square foot, and they've got a flat roof on it, and it's $9 per square foot for the roofing. And it's got to have a height of at least 6 feet. The volume is going to be 4,500 cubic feet, 4,500 cubic feet. What dimensions will minimize the cost of the silo? Before we go on, let me also mention this minimum at least 6 feet. Well, why that? Well, you want a reasonably sized person to be able to walk in there without having to completely bend over too much, and get in there and clean it out or get into it if we need to. And some of those considerations were true here for the soda can as well. I mean, had the maximum thing turned out to be really real short and wide, you couldn't get your hand around it very well. If it's really tall and skinny, that might not work very well either. So there are some considerations based on the human hand. There are also some considerations based on, Coke is going to want to make sure they get their logo on there. Okay, so there are some marketing considerations as well as some physical limitations that may come into play as well. Okay, so why don't you work this one out? Come back and check your answer with me in a few minutes. Press pause now. Well, it's very similar to the last problem. The volume's fixed at 4,500 cubic feet, so the volume again is pi r squared times h. So again, h is v over pi r squared. That's 4,500 over pi r squared. The cost is based on the area. 6 times the floor area plus 5 times the wall area plus 5 times the roof area will be the dollars of the cost. The cost is, so the floor area is pi r squared, so that's 6 pi r squared. The wall area is the circumference, 2 pi r, times the height, so that's 2 pi r h times 5. And the roof area is I said $9 per square foot, and I've got 5 here. Tell you what I'm going to do. I'm going to do something you can't do when you're the student. I'm going to change the problem. Okay, when you're a teacher, you can change the problem. When you're a student, you can't say, I don't like that problem. I want to do another one. But when you're a teacher, you can get by with that. So I'm going to change that to 5 so I don't have to change what's below. 5 times the roof area, so that's 5 pi r squared. So that makes 11 pi r squared here when I combine those two. And this makes 10 pi r h. H is 4,500 over pi r squared. And so we get this expression here as cost as a function of r. Take the derivative, very similar to the last problem, 22 pi r. And this is negative 45,000 r to the negative 2. Set that equal to 0, and again I'm going to multiply by r squared to get rid of that r to the negative 2, and I get 0 equals 22 pi r cubed minus 45,000. Add 45,000 divided by 22 pi, I have to cancel the 2 out here, and then take a cube root, and that's r to the 1/3 power, which is approximately 8.667, and that is in feet for r. And the height, then, if you plug that in here, this formula here, you get about 8.66 feet, which is tall enough. That's the R. You get 19 point something feet. And at this point, the cost is given by what? Well, you take that R and plug it back into this formula right here, let's say. This one here, it's underlined. And you can figure out the cost. And it turns out to be about $7,787.96. Okay, here's another one that we'll maybe do in the next video. Suppose this time the storage building is in the shape of a square pyramid instead of a cylinder. The cost of the concrete floor is $5 per square foot, and the walls are $3 a square foot. The volume is 4,876 cubic feet. What dimensions will minimize the cost of the building? See if you can work that one, and we'll check that answer in another video a little bit long down the line.